Welcome, ladies and gentlemen. This is video number 3 in our matter and measurement unit, specifically the measurement half of that. So you'll need your notes opened where it says video number 3. You'll also need a calculator and definitely your reference table. So in this video, I'm going to be talking about percent error and density. Now, error in general, obviously we kind of know that means like what's wrong, right? So, but you have to know what you're comparing it to. Like, how do you know if something is wrong? Well, you must know what the correct thing is. So accepted value, that's what we're going to start with error. The accepted value of something is the correct value of that thing. And how do you know it's the correct value? It's based on reliable references. So this is a bit of an implication to something that you look up on a reference table. We can use our own reference table. We can also use accepted reference tables, the other reference tables in chemistry. There's something called the CRC Handbook of Chemistry and Physics. That's basically this enormous reference table. You can look stuff up online for accepted values. And it's things like boiling points, melting points, densities, etc., etc. An experimental value is obviously not an accepted value. It's a value that is measured in a lab. So it's something if we were doing an experiment and you worked out, let's say, the boiling point of water, maybe your numbers tell you that the boiling point of water is, I don't know, 102 degrees Celsius. Well, that's not the accepted value, that's your experimental value. Error is quite simply the difference between your experimental value and your accepted value. That's what error is. What is the difference between the real thing and what you measured in the lab? Now, error can be positive or negative because it is always going to be experimental minus accepted. If it's a positive error, that means the experimental number was too big. It was bigger than the real thing. If it's a negative error, that means that your experimental value was too small. It was smaller than the real thing. And percent error, which is on table T, on your reference table, is calculated by taking the difference, so that's your error, your experimental minus accepted, and then dividing it by the accepted value, and then multiplying it by 100. So it's your percent error. So as an example of this, what's the percent error of a measurement of 955 Kelvin as the melting point of aluminum? Well, we want to follow this formula right here, experimental minus accepted over accepted times 100, and they gave us, it said, a measurement of 955 K, which means that this is the experimental, meaning you measured it. So we know that we need 955 Kelvin minus the accepted value, but the problem doesn't give us the accepted value. Oh, hey, melting point of aluminum. Maybe we look it up. And that's going to be in table S. Table S on your reference table is quite literally the most referencey portion of your reference table. It contains a listing of a whole bunch of accepted values for the different elements on the periodic table. So we want to look it up on table S. You want to find aluminum. Then you want to go over and find the melting point of aluminum. And we look it up, and the accepted value is 933 Kelvin. So then we can plug that in to the rest of the formula, 955 minus 933 over 933. When you're doing this math, do the top portion, do the numerator portion for it first, get a number, hit enter, and then do divided by 933, then hit enter, then do times 100. When we do out this math, I get 2.35798, and the number just keeps going. Now we want to round this to the correct number of sig figs. So how many sig figs should our answer have? Well, 955 is the number in the problem, so that's what you want to base it off of. 955, there are 3 sig figs in this number, so I know I'm going to need 3 sig figs in the answer, right? It's the same as the least number. So you always take the first 3. So 1, 2, 3, I'm going to keep those, I'm going to chop it off there, and then I'm going to think about rounding. So I'm going to look that one place out, and the one place out is that 7, and that is higher than 5, so I'm going to round that number up. So 2.36%, that's the percent error. Density is mass over volume, which I know you've seen before. Density is not new. We've done density problems before. And this equation is given on table T, just in case. Table T is where all of our formulas and equations are. So it's mass divided by volume. The units for density, because density is quite literally mass divided by volume, are units that imply mass divided by volume. So grams per milliliter. Per means divided by. That's quite literally what per means. grams per milliliter, grams divided by milliliters. We can also write it as grams per cubic centimeter. Same thing, per means divided by. Cubic centimeter is actually the exact same thing as a milliliter. It's actually the definition of a milliliter. 1 cubic centimeter, take a centimeter cubic, you got a milliliter. So those units are actually interchangeable. Now, density, just as a reminder, is an intrinsic property. What an intrinsic property means is that it does not change with the size of the thing, i.e. 1 gram of copper solid versus 100 grams of copper solid at the same temperature would have the exact same density. It's an intrinsic property. It doesn't change with the size of the thing. That also makes it a physical property. Density is not about how something reacts. It's just a quality about the matter itself. How many grams per cubic centimeter, not does it react with oxygen or does it react with hydrochloric acid. It's just something that you can observe without actually changing the thing itself. But density absolutely does change with phase of matter. It matters what phase of matter you have. Solids are typically the most dense phase of matter for a substance, then liquids and then gases are least dense. But that is typically. There are some notable exceptions. Hopefully you can kind of think of a really big one. Water. Water is a huge exception to this. Solid water is actually less dense than liquid water. That is why ice floats, because ice is water. It's just solid water. But it's less dense than the liquid phase of water, which is totally weird, by the way, guys. Water is weird. Water is bizarre that water does that. There's only one other thing I've ever come across that does that, and that's bismuth. Like, what? Who's heard of bismuth? What? Bizarre. Like, water and bismuth do that, and that's it. That's about it. So density. Density with particle diagrams. So we can sort of draw things with greater or lesser densities with particle diagrams. Because if particles are closer together, then that's going to show that your substance is more dense. They are quite literally more densely packed, because you have to remember that each particle that you draw is a tiny, tiny bit of mass. So the idea is that if we kind of draw one square here, and I'm going to try to make it the exact same size square in all three, and then you look at how many particles are inside that square, right? We got lots of mass per volume here, and we have less particles, so less mass per volume here. The volume is the square, so it's the same volume, it's the same size of space, but you have less stuff, so this is most dense. The particles are packed most closely, and this is least dense. There's not as much mass for the same volume area. And this is also generally representing, this is definitely a solid sort of representation, and this is really looking more like a gas over here. Now, density, the final thing about density is that, again, table S lists a whole bunch of accepted density values for the different elements on the periodic table. So we can have a question like this: what is the mass of a piece of scandium? So we're going to be looking up scandium, which is Sc, right there, that has a volume of 4.3 cubic centimeters. So it's asking for mass. What is the mass? And it gives us that the volume is 4.3 cubic centimeters. And we know that density is equal to mass divided by volume, but we don't have the density. So what do? We look up the density. You look it up. If you come up to me on a task and you're like, Mrs. Julian, you haven't given me enough information to solve this problem, I'm going to smile politely in your face, laugh to myself, and then walk away. Because I have actually given you enough information to solve this problem. I've given you a reference table, and you're meant to go look up the density of scandium in table S. So you go and you look it up. Densities in table S, it's 2.99 grams per cubic centimeter. So then we're just going to plug that stuff in. So we have the density, that's 2.99 is equal to the mass, we don't know, over 4.3 cubic centimeters. To solve this, you want to cross multiply, right? Cross multiply, do your little bow tie thing. So I'm going to be doing 2.99 times 4.3 is equal to 1 times the mass that we don't know. So when I solve that, I get a mass value of 12.85 0.57. Now, what unit would that be? That's going to be in grams, and I know that because of the density unit, the portion of this that is mass is the gram component. So I'm going to keep that as grams. But then I want to round to sig figs. So I want to think about sig figs. So the numbers that I have in my problem, I've got this number here, which has 2 sig figs. And then I have this number here, which has 3 sig figs. So how many sig figs should our answer have? You always go with the smaller number. So I need to round this to 2 sig figs, right? 2 sig figs. So what 2 sig figs are we going to keep? We're going to keep the first one and the second one, right? I'm going to keep those, and then I'm going to cut it off right there. But I have to look one more out in order to think about rounding. So this is an 8, so I am in fact going to be rounding up. So I'm going to report my mass to 2 sig figs as being 13 grams. And there we go. So we're going to take the opportunity to practice density problems and percent error problems in the context of rounding to correct number of significant figures.